Welcome to Basic Mathematics Analysis class. Today we will discuss some of the algebraic properties of real numbers. The real numbers. The algebraic properties of real numbers. Algebraic properties. The algebraic structure the algebraic structure of the real number system is the field with respect to addition and multiplication. Addition and multiplication. So we want to know what is a field. The algebraic structure of the real number system is the field, F-I-E-L-D, with respect to the addition and multiplication. You might have come across the term field in your algebra classes. If not, we can have the definition here. So I'm starting with the very fundamental binary operation. Binary operation. So binary operations, let S be a set and A comma B belongs to F. Then the binary relation A star B is defined as a map from S cross S to S. Thus, for each pair A comma B, there exists a unique element from B of AB in S. Okay. For example, we can take set of integers, and I am representing the binary operation here as addition. So addition. So whenever you take two integers and add it, again you will get a member in your set, right? So this is an example of binary operation. You can have a lot of binary operations. Uh, in Q, you can take A plus B by 2. Another binary operation. If you take two rationals, add it, divided by 2, you will get again a rational number. So such that operations, we will say that these are going to be binary operations. Notations. For A comma B belongs to real number, we denote A plus B as usual addition, and A dot B as usual multiplication. So we are having addition and multiplication. We are representing that as A plus B and A dot B. Next we are moving to the definition of group. A group G star is a set G closed under a binary operation star such that the following axioms are satisfied. That the following axioms are satisfied. So group means it's a set together with a binary operation which satisfies certain axioms. First axiom is we are naming as G1 for all ABC belongs to G. We have A star B star C is equal to A star B star C. It's called associativity of star. Associativity of star. G2 there is an element E in G such that for all X belongs to G, E star X equal to X star E is equal to X. It is called existence of identity. Existence of identity. Now G3 corresponding to each each A belongs to G, there is an element, there is an element A dash in G such that A star A dash, which is equal to A dash star A, which is equal to the identity. This is called existence of inverse. Existence of inverse. So this is the axioms that a structure G star should satisfy. Means we will say that structure to be a group. So group G star is a set G closed under a binary operation star such that the following axioms are satisfied. First axiom is associativity. That is A star B star C should be equal to A star B star of C. And G2, there is an element that is called the identity element. Okay, so existence of identity element. There is an element E in G such that for all x belongs to G, E star x equal to x star E equal to x. And G3, corresponding to each A belongs to G, there is an element A dash in G such that A star A dash equal to A dash star A equal to E. That is the existence of inverse. For example, we can take set of integers. Very easy one only I am taking. Set of integers with respect to addition. Now with respect to addition means we want to have three conditions. One is associativity. You take the elements from Z. For example, you take 3, 5, 6 from Z. Now 3 plus 5 plus 6 should be the same as 3 plus 5 plus 6, right? So this is called the associativity law. Okay, so when you're taking any arbitrary elements A, B, C from Z, and if you are getting A plus B plus C equal to A plus B plus C, then we will say that it is associativity. Now, existence of identity. What should be the identity there? So identity means evidently 0 belongs to Z. Okay, such that 0 plus some P equal to P plus 0 is equal to P for every P belongs to Z, right? So this existence of identity. Now existence of inverse. Existence of inverse means for every P belongs to Z, we can find minus P belongs to Z, right? Such that P plus minus P equal to 0 and minus P plus P is also 0. Now we will say that this minus P is the inverse of P with respect to addition. So existence of identity, existence of associativity, and existence of inverse. This together implies that Z plus is a group. It implies Z plus is a group. Next definition is abelian group. Or Another name is commutative group. If in a group for all a comma b in a group G, for all a comma b belongs to G, if a star b equal to b star a, then G is called an abelian group. An abelian group. Okay. For example, again you can take Z plus. Okay. Example, you can take Q plus also. Q plus. Now in this Q plus, if you are adding any two rationals, A, B belongs to Q, what you will get is A plus B should be same as B plus A, right? Then this is an abelian group. Now, on the set of real numbers, there are two binary operations denoted by plus and dot and called addition and multiplication and multiplication respectively. These operations satisfy the following properties. What is the first property means? A1 we will mention. A plus B equal to B plus A for all A comma B belongs to R. What is this property? Commutative property, right? Commutative property. Secondly, A2, A plus B plus C equal to A plus B plus C. This property is for all A comma B comma C belongs to R. This property is associative property, right? Associative property. Third one, existence of additive identity. What is the additive identity in real numbers? 0. Okay, that is there exists an element 0 in R such that 0 plus A equal to A plus 0 is equal to A for all A belongs to R. And fourth one, therefore, existence of negative element. Existence of negative element. Existence of negative elements. For each A belongs to R, there exists an element minus A in R such that A plus minus A equal to 0 and minus A plus A is equal to 0. So what does this all in axioms will indicate? A1 commutative property, A2 associative property, A3 existence of identity, and A4 existence of negative element or the inverse image. So this A1, A2, A3, A4 together implies real number with addition is an abelian group. Okay, that we can name it afterwards. And some more properties are there. I'm mentioning it as M1. A dot B equal to B dot A. Again, what is this? Commutative property, right? Commutative property for every A comma B belongs to R. Second one, again, A dot B dot C equal to A dot B dot C for every A comma B comma C belongs to R. So this property is called associativity. Associativity of dot, we can say. And third one, M3, there exists an element 1, there exists an element 1 in R distinct from 0 such that 1 into A equal to A and A into 1 equal to A for all A belongs to existence of unit element. Of unit element. And fourth one, M4, for each A not equal to 0 in R, there exists an element, 1 by A in R such that A into 1 by A equal to 1 and 1 by A into A is equal to 1. It's nothing but existence of reciprocal. Now the last condition, D, A dot B plus C is equal to A dot B plus A dot C, and B plus C dot A is equal to B dot A plus C dot A. This is called, for all A, B, C belongs to set of real numbers, this is called the distributive property of multiplication over addition. Distributive property of multiplication over addition. Distributive property of multiplication over addition. Now, from these properties, we have first one, R with operation of addition is an abelian group. From where you are getting? From condition A1, A2, A3 and F4. That is, condition A1 says that commutativity. A1 commutative property, A2 associative property, A3 existence of additive identity, and fourth one existence of inverse. So these four conditions says that R is an abelian group with respect to addition. What about M1? M1 is commutative property of multiplication. M2 again associativity. M3 existence of unit element, and M4 existence of reciprocals. So these four together implies that it is an abelian group with respect to multiplication whenever you are taking the non-zero elements. So second thing, the non-zero elements of R is an abelian group with respect to the operation of multiplication. with respect to multiplication. We are getting this from M1, M2, M3 and M4. Okay. Now what about the last one? Nothing but distributive property of multiplication over addition. That is, third one what you are getting is multiplication is distributive over addition in the set of real numbers. Now these three are together called field axioms. Not so you can have this as a remark. The remark. So we are having 9 conditions. These 9 conditions together we will say the field axioms. So not one, the above listed, the above listed 9 properties are known as the field axioms and our structure or with addition and multiplication is called a field. It's called a field. Second one, not two. So field means an algebraic structure which satisfies these 9 properties. That is, with respect to addition, it should be a group. With respect to multiplication, the non-zero elements of that set should form a group, and multiplication should be distributive over addition. These 3 conditions together implies that R is a field. Note 2. We can derive more algebraic properties of R from these field axioms. From this field axioms. So we can represent or we can derive more algebraic properties from these field axioms. So today we have discussed about, first of all, we have discussed about the algebraic properties of real numbers. For that, we have defined, or we have a quick review of what is the binary operation. Yeah, we have started with a binary operation. Then it's an operation from S star S to S. We have taken one example too. Then we have come across the definition of a group. A group is a set together with a binary operation which will satisfy the 3 conditions: associativity, existence of identity, and existence of inverse. For that also we have considered some examples. Now for abelian group, a group which is commutative means we will say that that's an abelian group. Again we have seen example. Then we have having the field axiom of real numbers. That is, in a short, we can say that R plus is an abelian group, R dot is an abelian group, and multiplication is distributive over addition. If the three conditions, we will say that it's a field, and these axioms are called field axioms. Now from N naught, thus R plus dot is a field, and we can derive the more algebraic properties from your next class onwards. So thank you for your patient listening. Thank you.